Hi everyone, welcome back to the AI in Healthcare webinar series. After the extremely informative session 1, we will now move to the second session. In this session, we will be focusing on the impact of AI on disease diagnostics and drug development. So without further ado, I would like to welcome our first speaker for this session, Dr. Ece Özkan Elsen. Dr. Ece obtained her PhD degree in 2018 from ETH Zürich. During her PhD, she has tackled problems of image reconstruction and image processing for cancer research. The goal of her doctoral thesis was to explore methods to characterize biomechanical properties of soft tissues using ultrasound. Her focus was on complex optimization methods and inverse problem formulations. She is broadly interested in probabilistic models, deep learning, and image processing to tackle medical problems and interpret medical data. Since March last year, Dr. Elsen holds the position of postdoctoral researcher in the Medical Data Science Group led by Professor Dr. Julia Vogt at ETH. She is also the co-leader of the Network of Women in Computer Science. Thank you for joining us today, Dr. Elsen. The stage is yours.
Can you hear me now?
Yeah, much better.
Okay,
Thank
perfect.
you.
Perfect. Hello, everyone. Thank you for inviting me for your event. I'm really looking forward to my talk and also the discussion afterwards. Today, I'll talk about an introduction to machine learning for healthcare. And before we do that, briefly discuss, talk about myself, what I do, and so on, and an overview about machine learning in general, then for healthcare, and give some examples what has been done, what has been going on, and also some future directions that one can tackle. So about me, I was born in Istanbul, so I'm from Turkey. I went to high school. Until high school, I was in Istanbul. Then I I came to Switzerland, did my bachelor's, master's, and PhD in ETH Zurich. I studied electrical engineering. I'm not actually from computer science, but I did electrical engineering. And then I worked in between for 2 years as a consultant and came back to academia last year. And I have a daughter, so I also have a new role as a mom and trying to balance the things out also. In my spare time, I like to run. We do relay runs also as a group. Actually, 2 weeks ago, we run as the whole research group as 110 kilometers and 14 people. That was actually really fun. I also like to travel. Recently, or actually not so recently anymore, 3 years ago, I had the longest 45 seconds of my life. Did a free fall from a plane, which was cool. And I also like to, as you mentioned, I'm also the co-leader of Network of Women in Computer Science. It's actually a really important role for me. We want to enthusiast more girls in computer science or any technical engineering or STEM actually. But we can talk about this later. So let me start my talk. There have been many successes of artificial intelligence and machine learning recently. One of the actually probably the biggest example or biggest thing that happened was the Google's DeepMind, where for the first time a computer, the AlphaGo, played or won against a human person without handicap in a full-size board, and I think that became actually quite big, and things accelerated also with that. There has been also quite some effort in different areas, such as, for example, protein structure prediction, or using AI to create new impressional paintings with guns. DeepL or Google Translate for translation. Spam filters, as we all know, for our mails, and self-driving cars. So let's probably maybe start with some concepts, because you probably hear quite many concepts. So what is artificial intelligence? Artificial intelligence is the broadest term, and it is not a big thing. It has been in the research pipeline already since 1950s, Anything with simplistic handwritten rules in a computer could be also can be seen as an artificial intelligence, or a board game. A computer playing a board game could also be seen as an artificial intelligence. The smaller group of that is the machine learning part. Machine learning is something that you teach the machines how to solve some problems, some questions. And the smaller group of that is the deep learning, and it is probably now the big thing that is currently happening in the research, using neural networks and other things for solving problems. So machine learning has close ties to statistics and applied mathematics. It is not only programming, but actually has some background in the applied mathematics and statistics. And its fundamental goal is to design a computer program or algorithm that learn to perform certain tasks in an automated manner. So how does it do it? So it observes and interacts with the surrounding world by the use of available data. So imagine we have available data on the left side, then we give it to our learning algorithm that learns it, and then we apply it, and using the observations, patterns, and regularities. So typically, these algorithms distill some observations of complex phenomena into a general model. Now I'd like to talk about the real topic, the machine learning for healthcare part. Why is it happening now? There has been, or why is it happening now in the healthcare? When you look at the modern hospitals, most of the modern hospitals have the computer-based systems as their integral part, with numerous routine activities, medical record keeping with electronic health records, imagings, as CT, MR, ultrasound, PET, anything that you can think about, and patient monitoring. With that, there has been actually quite some data and quite some digitalization happening in the last years. But actually, machine learning for healthcare is not a new thing that has happened in the last 10 years. There has been already an iconic example called Mycin, which was developed in 1972. It was an expert system used for diagnosing blood infections, and it included 450 hard-coded rules. So actually, our machine learning for healthcare has been, or the attempt has been with us for some time. And why is it? Why does the research have it now even more? And I call this, I think, because of the GPU revolution. It's probably because the computing power got way cheaper than it used to be, because you can use the GPUs for really simple calculations that you can do. And since this computing power became cheaper, the research also has accelerated in that. When we talk about machine learning, there has been some efforts in different directions. And I'd like to give you some examples how one can do as an overview, and then we'll give you some example specifically for healthcare part. So let's talk about the supervised learning part. For supervised learning, we have labeled training samples, and we learn a function as known as a model that maps an input to the correct output. So how is it done? Let's imagine we have features on the left side, as you can see, and they are labels to it. That means on the left side, we have features of banana, and the label tells it's a banana. When we have apple, and it says an apple, and so on. So we have our training data. Then, using this information, we generalize this information in a model or as a function. And when we have an unseen data point, like this one that is coming now to the scene, then we look at it and say, okay, does it look like a banana? No, not really. Does it look like an apple? No, not really. It's not exactly the same, but it actually looks closer to a dog. So that must be a dog. So this is how the supervised learning is being done. And by the way, if you have any questions in between, don't hesitate to ask. We can also do it that way. And so if there's supervised learning, there should be also an unsupervised version of it. And I'll briefly discuss the unsupervised supervised learning example. So this time we don't have any labels. In the previous one, we had the features on the left side and the labels on the right side. This time, imagine we don't have any labels. So we have training data as a gathering of some data, some dogs, wolves, pineapples, bananas, and so on. Now we give this to our model and expect that our model self-discovers some patterns in between. So our model looks into it and says, oh, okay, these things on the right side, they have 4 legs. The other ones, they don't really, they're not really part of it. Actually, I can cluster these into 2 groups. So this is what is being done. So it discovers some patterns that there's some data points are closer to some to each other and some others are not. So we saw 2 different examples or types of learning problems, and maybe we can discuss about when to use what in the medical setting. For example, an example of a supervised learning problem could be diagnosing and referring patients with retinal disease based on some scans, or predicting COVID-19 diagnosis based on some symptoms, or predicting mortality of patients based on some clinical variables. So these would be all examples of supervised learning because we would have some labeled data. We have clear end targets, and we have simple problem definition. So we have, I always said, based on something. So we have some variables, and then based on these, we predict a diagnosis or a label. So that would be the supervised learning example. And maybe we can also briefly discuss the examples of unsupervised learning in healthcare settings. So for example, discovering heart failure phenotypes based on some unstructured medical record data, or discovering novel subgroups of adult onset diabetes, or identifying groups of decliners among patients at risk of Alzheimer's disease. So we don't have, for these examples, we don't have access to labels. We often have an open-ended research question. So we are kind of looking something in the data we want to discover, but we are not sure what we are going to get. And we discover, so to say, novel patterns. And there has been actually really good recent examples in machine learning for healthcare in the supervised learning setting. Actually, the further slides, I'll mostly focus on supervised learning because I also work on supervised learning setting. So one of the examples was using chest X-ray data of patients to classify their common thorax diseases. So there has been labels for 14 different diseases, chest diseases, and using chest X-ray, this has been classified. And actually, really good performance has been achieved, actually almost at specialist level with the machine learning algorithms. And similar one was for the skin cancer diagnosis. They actually achieved dermatologist level classification of skin cancer. And in another example is the diabetic retinopathy diagnosis using fundus photography. So these has been all are mostly done with deep learning algorithms. I'll not go into detail, but if you want, we can discuss it later. So how does a typical supervised machine learning pipeline looks like? We mostly have a training data, as you can see. On the left side, we have some features that could be some clinical variables, tests, images, that you can think any data point that can be. And with that information, we always have for each feature point a label. So if the person has a disease or not, for example. Then we learn a model using this information. So we think about some mathematical like optimization kind of thing, or a model, or it can be CNN, it can be regression model, it can be random forest. You can think about different models. I'm going to talk about it later. Once we have the learned model, we have our validation data. So we look with our validation data that we didn't see until this point and check, how does our learned model look like? We get an error, we evaluate it, we get an error, and see, am I okay with the error rate that I get with my learned model? No. Okay, then I update my model using that. And once, until we are not fine, we iterate it. So we try to get a better model using the training data, and then validate it with that. And once we are fine with the error rate, then we test our model on the test data. Ideally, we have separate test data and validation data. So in the end, when we talk about machine learning or any learning-based method, we want to learn a model that generalizes well. For example, a model that extracts the essence of the relationship between the features and labels and makes accurate predictions on unseen data. And then we evaluate model's generalization error on the unseen test data, which is the data that the model has not been trained on. So if you would like to get anything from this talk, that's the most important part. Never test on your training data, because I think this happens quite often. And it's actually very important to test the reliability of your model, or to convince others. You should always have a separate test data that you have never used. So what can be the examples of these model that we want to learn? For example, we want to imagine we have a patient that has difficulty in breathing, and we want to we know that the patient has difficulty in breathing, and we want to do a recommendation based on this information. So we either say go to hospital or stay at home. So we may present our sequential reasoning process as a decision tree to learn a model, for example. So we have a data for the patient, and this data point says, does the patient have difficulty in breathing? Yes or no? If it says yes, then we say go to the hospital. So the model proposes to go to the hospital. And if the patient does not have difficulty in breathing, then the model asks further questions. For example, is the patient bleeding? If yes, then it should go to hospital. If no, then it should stay home. In practice, we can learn such decision trees from the data and perform, for example, classification. And this approach is called tree-based learning because we can present the prediction process as a sequence of decisions or splits and visualize it graphically as a tree. You probably know Bob Ross. He likes to draw some trees. And so the decision tree models have actually quite many advantages. They are easy to explain, easy to visualize and interpret, and easy to apply prediction even without a computer, and work in a very similar way to human decision making. So it is one can explain it, and also if you work with doctors, for example, you can easily convince them about your decision. However, they cannot work with complex data. For example, sorry. For example, if we have images, then you cannot really do a decision or easier decision tree for your prediction or for your diagnosis. For that, researchers came up with different ideas. One of that is, for example, deep learning. So what you do is you have, let's say, an input layer, and you have different hidden layers that you don't see, and you assign some weights or some outputs to your different paths, and you evaluate them. You decide, oh, the person that I see is Mark. In the meantime, when you look at these different layers, one realizes that you actually learn different things in these layers. So, for example, in the first layer, you learn edge or corner detection. In the second layer, maybe you learn to distinguish different eyes or different nose, different mouths, so different features of the face. And then in the third layer, you start distinguishing maybe between the people. So this is the idea of these different layers. It is not always like this, but ideally you would learn different things in the different layers. So it's a bit more complex learning process. I'm sorry, I'm a bit sick. Sorry. The next is a bit more complex we can go. The next one would be the convolutional neural networks. So what you would do is in the different layers, you would convolve through the image, and then depending on different parts of the image, you evaluate it through the image and then say, do a classification, for example, if it's a tumor or not a tumor. So why it has been an interest for the machine learning for healthcare, and why does healthcare need machine learning? So we have some clinical applications, what we want to solve, and then machine learning research that is happening. And I see that they are actually a bit further away currently. They're like two hills that are not touching each other. With the I'm so sorry. With the clinical applications, we have clinicians, physicians, or medical researchers that are interested in solving some or diagnosis or solving some questions. And in the machine learning research part, there are computer scientists, statisticians, mathematicians, physicists that are working on learning some models. So the clinicians, or on the left side, the clinical applications part, there are complex data sets which cannot be analyzed with conventional statistical tools. And on the right side, machine learning researchers come up with complex methods that have not been applied in practice yet. So both sides kind of need each other, but it would be much more beneficial if they can actually work with each other, so that the gap is less, and the gap between these two important parts are being bridged. So this is one of the, I think, the future thing that the machine learning for healthcare is going. So I think there are now much more interest or collaboration happening to bring these models, to bring these valuable research to the practice, because otherwise they will be in the dusty parts of the library who people don't really care about if we cannot bring them to use. So the next part, I would like to talk about the limitations, challenges, and opportunities in machine learning for healthcare to give you some future perspective. So the first, and I think the most important part is, we know there's a big data in machine learning for healthcare, but having only data doesn't help us. We also need the labels and annotations for it, because without these, it is really hard to make use of it. So that's actually one of the biggest challenges we currently have with machine learning for healthcare. The other part is, there's again a lot of data. for example, for a patient, we have clinical data, we have radiological images, scans, we have pathological information. Maybe we also have genomic data about the patient. But how can we match all this information? So how to learn across the domains, different tasks and modalities, and that's the multitask or multimodality learning that the research is actually working on currently. The other part is the data sharing, privacy, and security. So as we all know, the data that one has access to, they are all private data, and you cannot easily share it with people. So when you work with medical data, you should be really careful what kind of data sharing and privacy settings you have. The next 2 points is actually what I work on, and I'll give a bit more information about it, what I've been doing, for example, for this. So the interpretable and explainable machine learning. What do I mean with that? When you see an image on the left side and you say, oh, okay, this person has this diagnosis, the doctors don't really believe what we say because they don't know how we came up with this decision, because they only see a black box model that gives them, yeah, this person is sick or this person is not sick. And I think it will be much more beneficial, or actually the research also is going to that direction, if we can explain our decisions to doctors so that they can account, so that we can increase the accountability for the decisions that the model makes. So this is one research direction. It's actually being going quite fast, or growing at the moment, with the interpretable and explainable machine learning. And the next one is fair machine learning. So it's a English to German translation. You see on the right side, I'll tell you what has been happening. So in German language, you have gender for different words. So for example, a cleaning person can be a cleaning lady or a cleaning man, and these have different meaning, or they are different different words. And the same for professor. You can say it the professor as a male or female as a word. And when you translate it from English to German, you see that the cleaner removed the rubbish is translated to the cleaner lady removed the rubbish. And the second part is the professor held a lecture on nanosurgery, which means the male professor held a lecture on nanosurgery. So you see that there is a bias, or the cleaning person should be a woman and the professor should be a man. So this is what we call with the fair machine learning, that the learned models should be fair between subgroups in the data, and you cannot have, depending on some attributes that the groups have, you cannot come up with different diagnoses because it's not fair. As an example, for example, if you have only a white person data for skin cancer, and then you give a black person data for skin cancer detection, if you only learn it as if the person is white, then this happens, or the person is black, this happens, then you kind of learn a different association with the data, and it's also not fair. And sometimes maybe you don't even have access to this information, or it's not fair to ask. So this is the fair machine learning aspect that one works on. And I'll also briefly discuss about my PhD and current research. And if you have any questions, we can also discuss on that. So I mainly work with ultrasound technology. Ultrasound technology is, most of you heard of that. It's a cheap, mobile, real-time, and non-invasive technology, which makes it an ideal choice for many applications. However, it has low SNR, so it's signal-to-noise ratio. So it's sometimes really hard to make some understanding of the images. That's why, since it's so cheap and easily accessible, you have much data to work on it, but it's not so easy to use it. So that's why there's a big interest for the for ultrasound based decisions. So one of the works that I worked on was using to detect tissue abnormalities during morphology. For that, we used ultrasound waves in two different directions. So let's imagine we have one wave that is going directly perpendicular to the plane, and imagine the wave that goes the first arrow you go is going not through a tissue that has tissue abnormality. Let's say you have a cancerous region here, and on the left side, the wave would, or the wave part would go through the cancerous region. And when you change the angle of the wave you send, which you can do with ultrasound, you send them with some delay, and then your wave would not go this time direct with 90 degrees, but with an angle. And when you check now on the right side how the right wave arrives, now it's going through the cancerous region and the left one isn't. And you use this information, or we propose to use this information to reconstruct the speed of sound or arrivals in different parts of the tissue to detect the tissue abnormalities. So this was one of the works that I did. It was not a machine learning based approach, but rather an optimization. But during my PhD, I worked more with ultrasound physics to detect the different tissue characterizations. Another work we did was using deep learning for landmark tracking in liver ultrasound images. So what we did was we'd like to track a part of the region, a part of the image in a video sequence, for example, a vessel. And this is useful for example, if you want to do a radiation therapy, and if you want to send a wave to a cancerous region, for example, you would like to know with the breathing motion where this cancerous region would be, because it will move, and it's important to estimate the next step, so to say. And this was a work for it. So we were doing some landmark tracking in the liver with ultrasound using Siamese networks to do the tracking. And I think there's an example here. Yeah, exactly. So this is how we do the tracking. And this is one example. And then, and if you want, we can discuss a bit more with that. The next one, these are the next examples are the ones that I have been working in the last year. One is the interpretable machine learning or interpretable neural networks for detecting heart disease in newborn using ultrasound. So we had ultrasound sequences from newborn babies, so their heart, and we would like to use this information to predict if the baby has a pulmonary hypertension or not. So first we started using only one view, but normally you, as a doctor, you don't only look in from one location, the heart, but from different locations. So you have different views of the heart. And we use this different information or different views. And for each view, we do a prediction. And then if they match, so we can actually check if all views match, or if we discard some that we are not confident enough to have a final prediction. And also we looked at their decision. So where does the model look to come up with their prediction? And this is, I think, this can be useful for the doctors, because we can show that, hey, look, we think that this person has this disease because we are looking directly at the left chamber, as you would also do in your clinical diagnosis. I think this is important, that we don't only tell them, yeah, the person is sick or not, but actually tell them, because of this and that, we decided for this. And our models show that they actually look into very similar attributes of the heart as they would do in their clinical practice. The other work that I've been working on is the fairness in machine learning algorithms. There has been an effort, or there has been some results reported that for different groups, for example, for different genders, we have different diagnosis correctness, or the true positive rates. And this is actually not okay. That means the model focuses on some groups to have their diagnosis more correctly. And so our goal was to have a method that debiases this unfairness in the model. So imagine you have a training data that you have from a center. and you don't know, but you don't know about the attribute that you will be interested in. And then you evaluate your learned model in another center, and then you would like to be, however, fair for different ethnicities, and you want to debias your model depending on different ethnicities or their insurance type. So the model should not have different diagnosis efficiency or diagnosis correctness depending on their insurance type of the people. That's actually the goal. So how do we do it? We learn a model that we don't know anything about at the beginning. So the model that you will learn would be biased. And in your validation set, you do the debiasing. So either you can do, for example, pruning, so you remove some nodes, or you use gradient descent ascent, so you remove the different weights, and afterwards you would come to your model deployment to a different center with different protected attribute that you will debias and then deploy your model for that. So so maybe a quick recap. So today we discussed about recent machine learning examples, talked briefly about supervised and unsupervised learning and recent examples in the machine learning for healthcare, how a typical supervised machine learning pipeline looks like. I gave a short overview about limitations and challenges and opportunities in future for machine learning for healthcare, and also my current research. So that would be it from my side, and I'll be happy to answer your questions.
Thank you, Dr. Elsen, for such a nice and informative talk. We do have some questions in the chat, so let me start with those. Sunita asks, what are the factors that are needed to be considered for better unsupervised clustering?
As I said, I think I don't really work myself as for unsupervised learning that much, especially not for clustering. But I think there is important to have thinking about how the distribution looks like from your for your data. For example, if you have a distribution that is similar in your data and then you test it afterwards to a different distribution, your clustering will not probably be very well. And then you should also think about your domain shift and so on. So this factor you need to think about.
Thank you.
Yeah.
Another question from Ananya.
Mm-hmm.
Could you tell a little bit about technologies behind 3D and 4D ultrasound?
Yeah. So for 3D, you would get like a, how you say, like a 3D model at the end. It's like I think there are different ways of doing it. So you either scan as a 2D and sweep it. So you have like a 3D array instead of a 2D array for the ultrasound, and then you sweep it through your body, and then you would get a 3D model. And 4D is with the motion with that. But I think these methods or modalities exist, but I don't think that they are actually being used that much because we didn't even solve the 2D problems yet. So it is really hard to use or make use of these 3D and 4D ultrasound. So because also the doctors, I think they are not super open for different technologies. I think they use it, but for their diagnosis, they would still rely on their 2D ultrasound images. Because I didn't work on it, but for example, during my PhD, there was a project that they were actually simulating ultrasound images, and they were giving really nice looking, sharper ultrasound images. And the doctors were like, no, we don't want to have these sharper, we are not used to using these. We want our speckly, much noisy ultrasound images because we are trained using these. So I think, yes, these technologies are nice, but I think the doctors can put in their really clinical practice, it will take some time. So I think these things are still very experimental.
Thank you. Ashwini has a question. So how, as beginners, can somebody learn about these machine learning models?
I think as I started learning, probably it's much easier to start with simpler models. For example, a decision tree or regression model, random forest, and so on. And then build up on that, because it's really hard to start with convolutional neural networks if you don't know what are the basics are about. So this is how I also learned about this and just build up on it. And I think it is also much easier if you kind of understand what is really happening. And I think this is what is currently a bit lacking in most of the people who are doing, for example, data science or machine learning, because there's a hype for that. But if you don't know what is happening behind, then it's really hard to make use of it. So I would definitely suggest when you are learning these, try to learn what is really happening, and maybe in a smaller version. You don't have to learn like these huge models at the beginning, but try to kind of have the understanding, also mathematical understanding, what is happening behind. I think this is what I would recommend to the beginners. And there are quite many nice courses that one can take, definitely these ones, Coursera or any other things.
Okay, thank you. Well, until somebody asks another question, I have a question. So in one of the examples for unsupervised learning, you mentioned that we could use it to identify groups of slow and rapid declines among Alzheimer patients. But in this case, how would you define slow or rapid?
I mean, you hope that, so this is the part that you hope that, let's say we have Alzheimer patients and you say you want to have two groups, because sometimes in the clustering examples, you can tell the groups that number of groups you're interested in, and then you hope that this is what is being learned, or maybe you can impose some. This will be the semi-supervised learning. Maybe you can impose some information into the model that some of the groups should have this attribution that you would like to have. That would be it. But in a complete unsupervised manner, I agree that it's hard to hope that at the end you end up in these two groups, because it's at the end the model is learning some connections between the models, between the subgroups, and maybe this is not the connection that it learns.
Right. Okay, thank you.